Hello. I'm audible? I'm audible? Sir. Audible, sir. Sohail, sir, I am audible? Sohail, sir, I am audible? Please give me feedback whether I'm audible or not. Please give me feedback whether I'm audible or not. Hello. Okay. Hello. We can start now. Okay. We can start now. A very good morning to all and welcome you all for the another GATE lecture series under the Prerna scheme sponsored by AICTE. Today we have with us a very young and dynamic faculty and a very eminent and well-known personality, that is Dr. Sohail Parvez sir. Dr. Sohail Parvez sir is an assistant professor in Anjuman College of Engineering, Nagpur. He is having more than 22 years of teaching experience and he published more than 15 research paper in various national and international conference. Sir is an active member of IST, AMM and ISET. So I request Dr. Sohail Parvez sir to continue with the presentation. Sohail sir, you can continue now. Sohail sir, you can continue now. Sir, your voice is not. Sir, your voice is not audible. You are not audible. Hello, you are not audible, sir. Sir, please unmute your mic. सर प्लीज अनम्यूट योर माइक. सर आपका माइक म्यूट में है.
Again.
Okay, now it is okay.
Now it is okay? Okay. Thank you. So very good morning to one and all present in this lecture, and I hope this lecture would be useful for your preparations in GATE as well as in the forthcoming general competitive exams. Myself, Dr. Sohail Parvez from Anjuman College of Engineering. Now, as far as the subject is concerned, outline of the lecture number 1, that means in the morning session, we will discuss thermal stresses, strain gauges. These are basically the important topics in strength of material subject. First, we will deal with the very basic, because since we don't know how much we are acquainted with the basics of SOM, that is strength of material. So just a brief say revision, so that we can directly before coming to the thermal stresses, we can have the basic things cleared with us. Load. Now when we say load or force, so it may be defined as an external agency. Now when I say external agency, it means material body will experience load from outside only. This is the very basic element in the strength of materials. When we say load, it is basically the external agency. When we talk about body, the body would be material body, not the human body, because all the studies are being carried over for the material bodies. say steel, say aluminium, say cast iron, say wood, say rubber, plastic. All these are material bodies. Now, again, I am repeating the thing. It may be defined as the external agency. The load is defined as the external agency, which changes or tends to change the state of rest or uniform motion of a body. And I think it causes deformation. Now, when it says, you can see, when it says it changes, it means that if I'm applying a load, with this little finger, say for example, if it is not moving, though some external force is being applied, but it is not moving. So it is not necessary that all the time when force is applied, body has to move, because it depends all on the magnitude of applied force as well as the inertia of the body to be applied with. So the amount of force, it changes. When we say changes, say for example, I'm applying the force in this fashion. So this is the force which can move this body. So this is how we can define and we can learn about load. So again, I am repeating, the load is an external agency which changes or tends to change the state of rest or uniform motion of a body. The next element is stress. In a very easy and conventional method, it is force per unit area. But basically, that is the mathematical expression, force per unit area in Pascal, megapascal, kilopascal. But when we want to understand the physical significance of stress, what is stress basically? Stress is nothing but the reaction offered by the body to the applied external force. Now, this reaction is nothing but the self-respect. Yes, it is self-respect. The stress in the body, not for human body, this is for material body. Suppose if we want to apply some force on this member, and if that applied force does not changes its shape, it means that the internal resistance offered by this body is large as compared to applied force. I think all of you are getting my points. So please try to understand these basic facts. So when we say some external force is applied, so what is stress? Internal resistance. So this internal resistance would allow the body not to deform under the action of external force. So this internal resisting force is known as stress. Now, why I am insisting on this concept? Because unless and until, because since we are much acquainted with the definition force per unit area, but that definition is a mathematical representation. When we say it is the resistance, when it is resistance has to come when some external load will be applied. Now, where it will resist? Across its cross-sectional area. Why not length? Say, for example, I'm applying tensile load. Over this body. In that case, either it will elongate, or say if I'm applying some compressive load, it will deform. But in both the cases, the resistive area or the resistance would be offered not along the length, but across the length, that is along this cross-sectional area pi by 4 d square. So this is the basic terminologies used in stress. So I repeat, stress is the internal resistance offered by the body to the applied external force per unit of its cross-sectional area. Now, different types of stresses, since when we say nature or types of stresses, it all depends on the nature of applied force. That is, if it is tensile, the stress would be tensile. If it is compressive, it would be compressive. If it is shear, so direct shear, it means two equal or opposite forces applied tangentially. I repeat, applied it tangentially. Say for example, if this is the body, if I'm applying this type of force, so this would be called as compressive force. I'm applying this type of force, this would be tensile force. But when it comes to shear, direct shear, it means that tensile and compressive forces were axial. The line of action of forces passes through the axis. But when it comes to shear, that it doesn't pass through the center. Rather, to be more precise, it passes tangentially. So this distance, this difference or the distance, having same magnitude but difference in direction and having some distance known as a tangential distance. Yes, and by virtue of this, the body may fail into two parts. The body may fail into two parts. And this is called direct shear stress. When we say bending stress, say for example, this is the simple beam. When I am applying some load at this point, and if some deflection is visible or seen, then we may say that it is bending. Now, when we say it is bending, whether it is good that a beam should bend of our house or building, no. So what we should do, we should design it in a way that it should not deflect. The resistance offered to this deflection is bending stress. Yeah, this is bending stress. The next one is a torsional shear, that is very common. So the twisting phenomena is this. So we are going for this. In shafts, generally in bikes also, we apply kick to start the bikes. So there it is, twisting or torsion is there. The propeller shaft in the automobile, specifically heavy commercial vehicles, so it is subjected to torsional shear. When two equal and opposite couples are applied, see couples, these are couples. So two equal and opposite couples are applied, it means that the body is subjected to torsion or twisting. Now the next element is bearing or crushing stress. You just understand this point as it is the localized compressive stress. Now when I say localized compressive stress, it means that the compression, say for example, I am putting my finger here on this mobile flap. So the load applied at this point, that is localized area, this area would be localized. Then the influence of this force over this localized area would be known as crushing stress. So don't try to misinterpret it. Crushing means the bottle, we have opened the cap and crushed it and then thrown it away. No, sorry, that is not crushing in mechanical engineering design. Crushing means the localized compressive stress. The stress which is being experienced by the nail, when we hit that nail against the wall, the stress experienced by that nail, penetrating nail, is known as a crushing stress. Or the rivet in the riveted joint, subjected to bearing stress. So this is the next element. And the last element is a thermal stress. Now, what do you mean by thermal stress? This is the topic of today's discussion. So I hope in short I have explained load, stress, and then types of stresses. I will come over to the thermal stress. What do you mean by thermal stress? So I think you just listen to me first, and then you can go through the PowerPoint. The very basic element in thermal stresses would be, suppose this is a rod. I think my entire screen is visible. I am also visible there?
Yes, sir. Yes, sir.
I am visible, no? Okay, thank you. Now, because I am explaining all this with the props. So, when we see thermal stresses, it means you just consider simple. This is a metal rod, steel rod is there. I'm applying some heat at this end. what was our basic inferences that we have drawn right from our childhood? Sir, whenever a metal is heated, it expands freely. Yes, that is true. Most of the metal. So when I am applying some heat, for some 10 minutes, 20 minutes, 30 minutes, whatever, it will expand to little extent, 0.01 mm, 0.02 mm. Then what will happen? If I am keeping this rod over a surface, I am heating this, in that case it will expand, and after 1 hour, 2 hour, it will return to its original position when it is brought back or cooled down to the original temperature, initial temperature. So it has expanded, and over the period of time it has reduced, or it has again acquired the same position. So this is the first case. Now the second case, just look at this say example, wherein I am restraining this particular same metal rod between the two supports now. So these are the two supports. And now if some temperature is elevated or some temperature is raised, then what will happen? Now Mr. Rod will try to expand and go beyond this support, and these supports will say, "No, Baba, I'll not allow you to go outside." So in this case, again the same definition of stress. Whether this rod number two, I'm asking this as a number two question, whether this rod will be subjected to some stress, number two, and this one, number one case, whether this rod was subjected to some stress. Now the answer would be very clear. Since in the first case, this rod was heated and no resistance was offered to its deformation or elongation, hence we can surely say in this first case there would be no thermal stress acting on this rod. Whereas in the second case, when we say, for example, when we say some temperature is raised, so obviously its elongation will be restricted by these two supports, then obviously thermal stress would be developed or generated in the rod. So this is the basic idea of thermal stress. Unless and until there is some restriction or some constrainment, there won't be any stress. Now just look at this example on the PPT. Say I have fixed this rod AB from one side, and if I am raising the temperature from the other side, so what would happen? The rod will expand. And definitely you just go through this. Some temperature T, original length of the rod, Young's modulus, that is the property of the material. Alpha is most important part in this section, that is coefficient of linear expansion, and the value of alpha is already given in our data books. You might have referred PSD data book or RBD Shivalkar sir's data book, so data book it is available. Then extension produced in the rod is delta L. Now you just see the case. Due to increase in temperature, there is an extension delta L. Now this DL depends on what? Number one, length of rod. Number two, the temperature from T1 to T2, how much temperature is elevated. That is, here it is represented, rise in temperature represented by T. And the third element is the characteristics of material alpha, coefficient of linear expansion. When I say coefficient of linear expansion, it means every metal has got different coefficient of linear expansion. Yes, and that's why it will vary with material to material. So the extension of rod is alpha into T into L. My dear, this is called free expansion. The expansion of this rod would be known as a free expansion, and this DL is also known as free expansion length or change in length due to free expansion. Now, when we want to say strain, it is nothing but change in dimension upon original dimension. So change in length upon original length. How much change in length was there? Alpha TL upon L. So alpha T. So this is the basic equation of thermal strain. Now, if you want to calculate thermal stress, then Young's modulus would be into the play now, would come into play. Then Young's modulus is equals to stress upon strain. So stress is equals to Young's modulus into strain. So this is the basic formula. I think you are getting my point. So this is the basic formula how we calculate thermal stress. Now, this is the another level, another case wherein we can see that when the same rod of length L subjected to some temperature T having alpha as coefficient of linear expansion. Now what will happen? See, if we restrain its expansion by putting a second restriction on this side also, and if the temperature is raised, now please mind well this word, this is very important word. Stress and strain when support yields. What is yield? What is yield? A small deformation. What is yield? Small deformation. Small deformation. So in this particular case, say for example for you, if this is the case, if I am applying another restriction, and if due to thermal expansion, what was the duty of these two supports? Not to expand themselves, only restrict the motion of this particular or expansion of this rod. But say, for the sake of understanding, say that this particular support itself yields. It means the total original length was L and the yielding is some del. This I have shown with this del. So this del would be subtracted from the free length, because if you don't have this restriction, say for example, for the sake of understanding, if this is the length of this rod is 100 mm, I'm hitting this rod, fixing from this end, I'm hitting this rod will go up to 102 mm. But what I have done, I have applied another support. 100, it has gone up to 102. First case. Second case, 100, I have restricted its motion. Now, if I increase the temperature, what will happen? It will not allow this rod to expand freely, but it will yield a slight yield, say 100.5 mm. So how will you write the total free expansion? Total free expansion, sir, it was 102. Right now it is 100.5. So the actual expansion would be written as expansion due to rise in temperature minus rise in temperature is alpha into T into L minus this. Yes, the actual expansion would have been gone 1.5 mm, but it is restricted. So actual strain is equals to actual expansion upon original length. That is actual stress. So this is the second formula. Generally, the questions are 1 mark questions on thermal stress, and these two formulas should be kept in mind. The next is composite bar. A bar made of 2 or more metals. A rod made of 2 or more materials. A section made of 2 or more materials are known as composite sections. When I say composite section, the best example is your concrete column, wherein steel rods are there. It is material number 1, and the concrete gravels are there, material number 2. That is the composite section. But in mechanical engineering, composite sections are used in shafts, in most of the machine tool elements, wherein our prime intention is to transmit, to dissipate heat, to dissipate heat. Yes, sir, to dissipate heat. That's why we generally go for composite section. Now, what is the basic idea of composite section? You just go through the next slide. Yes. Really about all this thing, you just concentrate on these three different categories of diagram. Original bar, a brass is inserted between two steel bars. Now, when I say one end is fixed, please and try to understand this fact. One end is fixed and the temperature is raised. Now, say for example, some temperature is raised, then in that case, the entire assembly will elongate. The entire assembly will elongate, will try to expand. But whether that expansion would be in compliance with the individuality of the material? No. Because as far as Young's modulus of steel is concerned, the Young's modulus of steel is higher. Please mind well. The Young's modulus of steel is higher than that of the brass. That in that case, if I'm applying the rise in temperature for both the metals, and in that case steel would expand less and brass would expand more. But what will happen? So the problem is since it is janam janam ka saath, yes, it is composite section now. So no one can act independently in that case. If for example, for a rise of temperature from T1 to T2, if steel can expand from 1 to 5, then for the same rise in temperature, brass will expand from 1 to 10. But if you finally see the assembly will expand somewhere in between 5 to 10. Because this steel will go up to 5 very easily, and after 5 it will tell to this brass brother, I cannot come after this limit because my expansion is over. Now brass will request to this steel, my dear friend, since I can go alone up to 10 units for the sake of understanding, but since you are also constrained and I am also constrained, so please cooperate with me. I am compromising from 10 to some lower value. You just compromise, since janam janam ka saath is there. So you just compromise and come with me or come along with me to some do char kadam, and then the things are done. Now when I say things are done, it means now the actual expansion of the steel would be higher than this designated value, and the actual expansion of the brass would be lesser than the designated value. So this is the basic configuration of thermal stresses in composite section. So I think the rest of the things you can very well see, because this I have explained. Two conclusions can be drawn: extension of steel plus compression of brass is equal to difference in free length. And number two, the conclusion number two, that is very important. Sir, that important is tensile force in steel is equal to compressive force in brass. Yes, it will apply. It will, again I am repeating, this brass will take this steel, so brass will apply tensile load on steel, and when it will try to go above this, the steel will apply a compressive force on brass, and the story is in front of you. So tensile force in steel. Now how this force can be written? So this force can be written as sigma, and obviously the strain would be same because deformation would be same all the way. So strain ES is equals to EB. So E means what? Sigma S into S, sigma B into AB. And so we can put sigma S into L upon E. So this is the basic fundamental equation for calculating any, say solving any numerical, that is small E1 strain, E1 plus E2 is equals to alpha 2 minus alpha 1 into L into rise in temperature T. So this is the basic of thermal stress. I hope you are getting the things. Now, these are some questions from your GATE examination from recent past, 2017, 2016, and I think one question is from 2011, which I have got. You just go through it. A steel rod of length L and diameter D fixed at both the ends is uniformly heated to a temperature rise of delta T. The Young's modulus is E and the coefficient of Riemann expansion is alpha. The thermal stress in the rod is. I have written the answer also, just for making you comfortable in answering the question. So what is the answer? E into alpha into delta, because thermal stress it is asking. So when I say thermal stress, you can go to our basic slide. Please see. See, this is the basic. So the same thing is repeated here. Same thing. Alpha into delta T into E. So this is the stress. Now the next. A steel bar is held by two fixed supports. These are the two fixed supports as shown in figure and is subjected to increase in temperature, that is delta T. If the coefficient of thermal expansion and Young's modulus of elasticities are this given, then the magnitude of thermal stress, again the same formula we can apply and we can get. So I have just given you for the sake of understanding. Otherwise you could have solved this. So this is the question number 2. Third is very important because it is basically connected with the understanding. A circular rod of length L, area cross section A has a modulus velocity E and coefficient of thermal expansion alpha. One end of the rod is fixed and the other end is free. If the temperature of the rod is increased by delta T, then stress developed in the rod is E alpha delta T and strain developed in the rod is this. Both stress and strain developed in the rod are 0. That is not at all true. Not at all true. Third, stress developed in the rod is 0 and strain developed in the rod is alpha into delta T. And next, stress developed in the rod is this and the strain developed in the rod is 0. Now, our basic understanding is unless and until there is some restriction on the free expansion of this rod, there can't be or there won't be any stress. Am I right? Unless and until there is some restriction, there can't be any stress. So stress is 0. But since some deformation is there, so if there is some change in length, there has to have some deformation, there has to have some strain. So that's why the option C is there. The option C is there. So please mind well. And the last one is again very important. So you can very well grasp it. An initially stress-free massless elastic beam of length L, okay, of length L and circular cross section D, okay, and obviously D is less than, is held between fixed between two walls as shown. Obviously the same diagram. The beam material has Young's modulus E and coefficient of thermal expansion E. So this is the thermal expansion. So in this case, what would be the required to cause, the temperature rise required to cause the beam to buckle is proportional to. Now, obviously, I have told you in the very beginning, that it is along the cross section. And when it says along the cross section, it means pi by 4 d square. It means pi by 4 d square, and that's why pi by 4 d square. So d square, this is the square actually, yeah? D square, d cube, and d raised to the power 4. The correct answer is d square. So I hope you have got brief insight of this particular subject or the topic, that is thermal stress. Now we shall move for the next topic of today's lecture. That is, the next topic is strain gauges.
Yes.
Now, what is strain? What is strain, and how would you measure strain? This is very important. And as far as definition of strain is concerned, we are much aware about the change in dimension upon original dimension. Now, when I say change in dimension upon original dimension, it means it is the ratio basically. See, for the sake of understanding, I'm taking this example wherein I can say that this is a rod of some length 100 mm. I'm applying some pull from the other end. This is say fixed. I'm applying some pull from the other end. In that case, it has an increment of 1 mm. It has an increment of 1 mm. So this increment of 1 mm divided by the original length, this is change in length divided by the original length, would give us a strain. What does it signifies? What does it shows? It shows that the percentage of elongation a material can have under the action of external force, and that is the characteristics of each and every material. That's why these strain, sir, up to 12 o'clock. So this is the fact. Sorry for the interruption, technical interruption. So the ratio of this change in length upon original length, it shows how material can be fatal, how material can be faithful or reliable. When some load is applied, it can elongate. Yes, the pipe on which our ceiling fan is hanged. Yes, the hook which is carrying tons of load in a crane, the cable, the lift cables. So strain and the measurement of strain is very important. The devices or the setups used to measure that strain are known as strain gauges. Now strain gauges, the basic principle is very simple. Say for example, if I am expecting, just see to this, if I am expecting, say, to calculate the deformation of this page. So this page is deformed now. I'm pulling it away. So what I'll be doing is I'll attach at two different points. I'll attach two metallic rods. And that rod is connected to some semiconductor element. Since we are from mechanical engineering, so I'm explaining in that raw manner. So what will happen if due to some deformation there would be change in resistances, in more precise way change in current, and this change in current would be calculated on the galvanometer. That's it. This is the basic. So that's why again this is strain is L2 minus L1 upon L1. So this is how now strain can be measured using various types of devices. So these are the devices: mechanical devices, optical devices, pneumatic devices, and electrical type. As far as mechanical devices were concerned, in universal testing machine, the change in length of this rod was measured by either dial gauge indicator or the extensometer, wherein this rod, specimen rod, we attach two probes of this extensometer. If there is a slight increment, so this increment will be noted at the extensometer dial or reading gauge. That's it. So this is the mechanical type of strain gauge. Electrical type is also there. Optical type is there. If you want to calculate the rotation RPM of the shaft, so both the type of devices were there. One is physical contact type. You might have heard the name stroboscope, RPM measurement. So that is the case. Now the basic element of any strain gauge is the change in dimension. A small change in diameter will be detected by that electronic circuit, and it will be shown on the galvanometer reading. Now, the physical deformation is converted into analogous current, and that analogous current is calibrated in terms of displacement of that particular rod, element, substance. So, effector is used in the calculation, in the measurement using strain gauges using strain gauges. That is gauge factor. That is a very important factor. Now, when I say gauge factor, it depends on change in the resistance. It depends on change in undeformed gauge length, basically. The resistance offered. And last is strain. So that is the gauge factor. This is the generalized, representation of strain gauges. If you can concentrate on the screen. So a metallic grid wire is there. Okay, that is called gauge length, the effective length or gauge length. And then it is basically soldered. It is basically soldered on the plates. And the gauge length and the strain gauge is defined as the sensitivity, obviously sensitivity length of the grid. If there is a small change in the length of this particular gauge, then that deformation would be recorded as the strain, as the elongation, and that's why the current and the parameters are fixed for this much amount or this much length of this particular gauge. If there is a small change, it will be reflected on the screen. The next topic is strain rosettes. Now, the basic problem with the general strain gauges, see, these strain gauges were basically applied for our boilers, pressure vessels. It was applied on the surfaces of that pressure vessels, boilers. Why? Because if the internal pressure of that boiler increases, the chances are there, although we use 3 to 4 times of factor of safety for the design of boilers, sometimes 5. Yes, sometimes 5 factor of safety was 5 for the design of boilers, but still there may be chances of accumulation of extra steam in the steam dome, and some technical fault may be there at the steam nozzle. And in that case of emergency, what would happen? Any untoward incident may happen. That's why we were using the mechanical as well as electrical strain gauges. Now, these strain gauges were fixed on the surface of boiler, and if there occurs a small deformation of the surface, then it should have reflected at the screen, and the pressure or the temperature can be lowered down, or the steam can be evaporated instantly, so that the entire setup can be saved from the accident. So those were the cases, but there was some limitation of the say the primary or basic strain gauges. The limitation was, it was not only affected by the characteristic of the material, but also by the surrounding temperature. The surrounding temperature may affect its deformation. Even though there is no deformation on the surface, but if the temperature is raised, then obviously, if it is a metal, then it will expand and it will show some error readings. To eradicate this problem, we have used strain rosettes. Now, strain Rosettes are basically the arrangement of strain gauges in arbitrary directions. Now, depending upon the arrangement, these strain gauges are classified as star strain gauge Rosette delta, that is most widely used as delta and rectangular strain gauges in our mechanical engineering, specifically aircrafts. Then your cables of Ramjula also you might have seen in shafts, in gears for their deviation. So we can use all say these applications. Now this is the basic arrangement of star strain. So it is like star strain having 120 of inclination between the two strain gauges, or known as, this arrangement is known as strain Rosette. So this is the strain at A, B, and C. That is at the angle. Now the strain gauges. Second type is delta Rosette, wherein this again the delta Rosette. The arrangement is as per the requirement, and again the rectangular Rosette, wherein we have three different inclinations. That is 0. Obviously 0 is the base, then 45, and then 90. So with this arrangement, we can accurately measure the strain on any surface, on any beam, on any shaft, on aircraft wings. And that is the most crucial part of the aviation. You have to measure the strain that is occurring on the aircraft wings. You have to measure the extension of your Ramjula cables. You have to take into consideration the wind speed, because it will again try to influence the deformation of that particular cables. So in that case, this would be the governing equations for the calculation. Another arrangement for again getting the faithful results, the arrangement is a V-stone bridge. In this arrangement also, this is basically the galvanometric arrangement which you might have studied in your first year. So this is very simple, wherein some resistances have been put, R1, R2, R3 and R4. R1, R2, R3 and R4. So, and some voltage is applied. Now this voltage at the input. Now, if these two probes, that is the output, if there occurs any deformation, now the bridge circuit is given below, I'll directly read it. Why? Because it would be very simple for you and for me also. It is a network of 4 resistors with an excitation voltage VEX that is applied across the bridge. The Western bridge is electrically equivalent of 2 parallel voltage divider circuit with R1 and R2. So this is 1 and this is divider number 2. As one of them, and L3 are there as the other side. The output of the Western circuit is given by, so this is the basic formula of any Western type of arrangement. Now, the equivalent strain output and voltage output always have a relation of 2:1. These are the calibrations. So any change, again I am repeating this fact. Say for example, I am applying these 2 probes on a certain piece. Here I have applied these probes of R2. Since I was knowing the resistance of R1, R2, R3 and R4, and at the output, that is at the VO, some galvanometer is attached, some ammeter, voltmeter is attached. I'm using the correct technical name, galvanometer. And galvanometer was showing 0. Yes, it has to show 0. And we say that the bridge is balanced. Now the moment we remove that resistance, or in physical term, if some deformation is there in R2, R1, R4 or R3, then it will change the resistance. And the moment it changes the resistance, change in resistance will be basically displayed on the galvanometer, and we say that, oh, some strain is occurring at this limb or at this section. So this is the basic idea. These are the some of the applications which I have discussed. Aerospace, Rail monitoring. Rail monitoring is the most widely used application of strain gauges. Then torque and power measurement in rotating equipment, that is turbine, motor shafts, engine, fan, generator, wheels, etc. Cable of the bridges. Cable bridges sense the wind speed and strain on its cable. So I hope some of the points are I have tried from my side to clear the basic idea of strain gauges. So strain gauges works on the basic principle of change in length, change in dimension. That's it. If there is a change in dimension, it will be reflected on the panel, and we can take the preventive action for this particular deformation. So we should end here with the strain gauges. Some of the questions, one or two questions I have just given for the sake of understanding the type of a pattern of the question. A self-temperature composition gauge can be used in general for. Now, when we say self-temperature, it means a specialty of that particular. So it cannot be used for any material, only for steel, only for a particular material. So the answer is A. That's why I have put it this question at the first, because it has been asked twice in the previous examinations. So accordingly, you should take into consideration. The next one is again very important. That is the question on your rectangular strain rosette. So you can see this. This is 10 to the power minus 6 actually. So I have written, but in PPT it is reflecting in this way. So this is the basic equation wherein strain at A, B, and C and the shear strain is calculated, and then using principal strain theory or principal strain formulae, we have calculated the principal stresses of this particular strain gauge, which has calculated. So the last topic for this session is strain energy. And now when we say strain energy, it is the energy stored in the body. Say for example, let us say this is a spring. Say this is the spring. If I'm applying some force or load, so it is deforming. It is deformed. So what is strain energy? Whenever a force, external force is applied on an elastic body, it deforms. Now when it deforms, how come it rebounds back? The energy which is stored while deforming, the energy which is stored while deforming is known as strain energy. The energy stored in the body while deforming is known as strain energy. That's it. This is the basic fundamental. Now during deformation, it says आज मेरा बुरा वक्त चल रहा है, आज तू भारी पड़ गया, मैं compress हो गया, but एक दिन मेरा आएगा, and that one day, that is the gussa, and that is the strain energy. It is acquiring, and now the same strain energy will be used to regain or to rebound back. That is called strain energy. Why I am going through all these definitions? Because these are the most important definitions in the subject of strain energy. Specifically, resilience, the total strain energy stored in a body. Total strain energy is stored in the body, or sometimes it is known as capacity of a body. How far you can store the energy. Say some springs are there, rubbers are there. It can deform up to 60%, some up to 50%, some up to 40% of their length. So it depends on resiliences. For example, let us take again the example of, say, this is a steel rod and this is aluminium rod. If these are two separate rods, if I am applying the same load on these two rods, say 10 kilonewton, 10 kilonewton, so it is quite clear that the Young's modulus of steel is larger than aluminium. So if I am applying 10 kilonewton on both the rods, then definitely and surely aluminium will compress or deform more as compared to steel. Yes or no? So aluminium is more resilient than steel, or steel is more resilient than aluminium? Steel is more resilient. Or steel is more resilient. You just concentrate on material resilience represents its ability to absorb energy without any permanent damage. So this is the resilience. Proof resilience, maximum strain energy stored in the body, is known as proof resilience. Modulus of resilience, again the same thing. You might have studied this in subject mechanics of material. Modulus of resilience, proof resilience per unit volume of the body. Now, how many types of loading are there? This is again very, very important. How many types of loading and how many different types of loadings are there? Sir, as far as loading is concerned, gradually applied load, gradually applied load, which we apply on the vehicles when it's not starting. Tug of war rope, we are applying gradual load. Suddenly applied load, the load which is applied, say on the weighing machine, we suddenly go, we never jumped. I don't know you are jumping over it or not, but we generally go and we suddenly apply our load. All of a sudden, the entire magnitude of load is being put on the pan. And third one is impact. So this is impact. The basic difference between suddenly applied load and impact load is very simple. I'm giving you with example. Say this is some load. I'm putting this load on this platform in this fashion is known as a suddenly applied load. But I am taking this body or rod in this fashion and I am dropping it down, means with some height. If I am putting it down, this type of load is known as impact load. So this is impact. Now these are the some expressions which are very much essential to explain the strain energy when the load applied is gradual. Now look at this graph wherein when we say gradual load at time t is equals to 0, the deformation is 0 and the load applied is 0. The moment we go on increasing the load, the gradually the extension or the elongation goes on increasing, and thus this is the graph. This is the graph basically. O to n is the graph. Now area under the curve is nothing but work done. What do you mean work done? How much work is done by this pulling load in deforming the body, and that is gradual load. So work done is nothing but area of load extension curve, or area under the curve. And the area under the curve is a triangular body. This is triangular body curve. So half base into height, height is P, base is delta L. So I have given the same thing. Now since these are the mathematical interpretation, load is equals to stress into area, and change in length is delta L is equals to strain into length. Work done, how much is the work done? So work done by the load is half. So you replace delta L, please replace delta L by strain into L, and replace P by stress into area. So we have replaced delta L and P in terms of stress and strain. Simplified the thing. So half, this is stress, strain and volume. Again we can say that strain is equals to stress upon Young's modulus. So we'll replace this strain by stress upon Young's modulus. So we have replaced this strain epsilon by this. So sigma half, sigma square upon E into A into L, and sigma square upon 2E into B. This is the basic expression for strain energy in body subjected to gradually applied load. The next one is for suddenly applied load. Now when I say suddenly applied load, the entire magnitude will be there. Entire magnitude will be there. So I can show you with the graph. I can show you with the graph that if we are applying some load that is sudden nature, then in that case I'll show you. No problem. Now in this case, I think it is visible. The graph is visible. The graph is visible. Anyone comment, please?
Yes, sir. Yes, sir.
Okay, thank you. So in this case, when I say at t is equals to 0, so everything is 0. But the moment at t is equals to some, at that instant, the applied load will shoot up and the graph would be in this fashion. Yes, it would be a rectangular graph then. It would be a rectangular graph then. So this is the rectangular graph for suddenly applied load, because in no time the entire magnitude is applied. Na? So this is p is equals to 0 to some p is equals to maximum. And after the application of load, deformation would start. So the deformation would be starting. So at this instant t is equals to 0, p is equals to p max, and then after that some deformation would start. So this is the basic graph of suddenly applied load. So in that case, area under the curve would be, my dear friends, area under the curve would be, sir, it would be a rectangular. So base into height, base is delta L, height is p. That's it. Previously it was rectangular, a triangular. Now it is rectangular. So p into delta L. And again the things are very much clear in the PPT itself. So now if you compare work done by the load, so work done we have already discussed. So this is the work done by the load p into delta L. Again we'll have to change. Please mind well. We'll have to change p. So we will substituting the value of p, delta L. In this case, what we'll be getting is sigma, because sigma into a. Okay, so we have changed this and we have got this. Work done by load is equals to, this will remain, left side will remain same, sigma square upon twice E into A into L is equals to P into delta L. We have replaced delta L. Okay, so again the same thing, we'll compare, and what you'll be getting is sigma is equals to 2 into P by A. You solve it yourself, you write it down. It's very simple. So we can say that as far as gradually applied load is concerned, and Mr. suddenly applied load, the stress produced in the body would be twice as that of gradual load. And it is true also, because when we apply sudden, it will have, when we apply sudden, not this is not sudden, sorry, if you apply sudden load, then obviously the entire magnitude is acting, and that's why the stress would be doubled. Manual stress would be doubled. And now the third case, impact load. Just allow me for 2 minutes, 2 more minutes. We are finishing it now, but before completing, sorry, I cannot turn off. Impact load. Now again, the impact or the shock load, same thing. Now consider a rod of some diameter d and area A. A free falling load is kept, load P is kept or is released from a height of h. Let L be the length of rod. A collar is attached at the end, and when this load strikes on the collar, there is change in length of this rod L, that is delta L. Now again we say, what is work done? Force into displacement. Now how much is the strain energy? The same, sigma square upon twice E A into L. This is the strain energy stored. But how much is the work done? भाई इस लोड ने कितना काम किया? Sir, the load has worked how much? This P has worked a deformation, a displacement of this P from H and delta L. That's why the relation P into H plus delta L. because this P has moved, has displaced from a height h, and it has again displaced this collar or entire rod by delta L. Now this is the basic equation. You again go on shifting and go on substituting the values. See, Young's model is equal to stress upon strain. So again, strain mean what? Change in length upon original length. Now you please substitute the value and you will be getting the answer. So again, the same thing, you will be getting this answer. So this is the quadratic equation basically. And what I feel that you should please concentrate on this aspect only. Sorry, you should concentrate on this aspect only. This one. That is stress is equals to load upon area plus minus load upon area under root of 1 plus twice AEH upon PL. But this is the final equation. This is the final equation. You might have studied or learned that example in mechanics of material, that is on strain energy, that where it is asked to compare or calculate the stresses. So I must tell you that if the same load is applied gradually, the stress would be 4.5 megapascal. If the same load is applied as a sudden, then the magnitude of that particular stress would be 9 megapascal. You might have solved that numerical. And the third case, impact. At some height of 50 mm, the same mass is dropped. In that case, the stress produced in the rod, not in the collar, in the rod, it was somewhere 213 megapascal. See the difference, 4.5 megapascal gradual, 9 megapascal sudden, and 200 and above megapascal for impact. So impact is very dangerous, and hence it is we are duty bound to be very careful while designing the components which are subjected to impact or shock loading. And that's why we generally go for the factor of safety is higher sides. As far as factor of safety is concerned, factor of safety may be in the range of 1.1, maybe minimum 1.1 or 1.05 or 1.12, or may go up to 16 also. So 16 times you can increase the dimension so as to make the product or the services safe. I hope I have explained the things, and I expect you all to go through this presentation once or twice, so that the basics of again the elements which have been taught, thermal stress, then strain gauges and the strain energy can be cleared. Thank you so much. Thank you for the patient listening.
Okay, thank you very much, sir. Students, do you have any doubt, any queries? Anyone want to ask any question to our today's expert? You can unmute your mic, or you can put your doubts on the chat box also. No doubts? Okay, I think, sir, there is no doubt from your side. So thank you very much, sir, for accepting our invitation and sharing your valuable knowledge to our students.
Thank you, sir. Thank you.
I hope students will definitely benefited from this lecture. And I think today we have again another lecture at 4 p.m.
Yes, sir.
So students will again meet today at 4 p.m. with Dr. Professor Sohail Parvez, sir. Thank you very much, sir.
Thank you. Thank you, sir.